Alright, so for this problem that was assigned in homework, this is how we're going to solve this. We're going to solve for this first and then apply it to this. So the first thing we got to find is the amount of the molality of the solution. We're going to take the starting amount in the problem of the solute, and it's 50.0 grams of this ethylene glycol. The formula I gave you is right here. I can write it in that form, or I can shorten it and say it's H6C2O2 if I want to. All right, whoever's making the noise, it needs to stop now. And actually, I'm missing a 0 here. And that should be over 100 grams of the water. So I've put it in the form where I've got the amount of solute over the amount of solvent, and whatever units of measurement are listed in the problem. What we need to do is to convert this amount into moles, and for that we need the molar mass. So we're going to have to add the atomic masses of all the atoms in the formula. We've got hydrogens and oxygens and carbons. And hydrogen's atomic mass is 1.00794. Oxygen's atomic mass is 15.9994. And carbon's atomic mass is 12.0107. All those can be found on the periodic table. That's the atomic mass for each. So we've got 6 hydrogens in the formula. So we're going to multiply this by 6. We've got 2 oxygens in the formula. Multiply that by 2. We've got 2 carbons in the formula. So we're going to multiply that by 2. What? Well, but it's not hard math, you know. Yeah. All right, so this is going to become 6.04764, and this is 31.9988, and this is 24.0214. I'm going to add these together. And if you'll note, I've been very careful with the digits, lining them up vertically so that I can see I've got empty slots right here. Add those together, and you're going to get 62.06784. And because that last digit came from empty slots, we round it off. We're going to underline it to show that it's insignificant. We're going to use an arrow to show that we're rounding off. Those operators have to be there. You get points for that on the test. And so we get 62.0678 grams of ethylene glycol. And that's equal to 1 mole of ethylene glycol. Okay. Now, the reason we do that is, with an equality statement like this, we can arrange it up here into a conversion unit that's going to allow us to convert from the grams of the solute to the moles of solute we want to have. So we're going to put 1 mole of ethylene glycol on the top here. And we're going to put the other side of the equality statement on the bottom. We arrange it this way with the grams on the bottom here only because we want to be able to cancel the grams here and the species here and leave ourselves with the moles of the solute that we're looking for. Now the same thing, we're going to do basically the same thing with what's on the bottom, only in this case we're converting from grams into kilograms. For that we're going to need another equality statement. The equality statement is that there are 1,000 grams in 1 kilogram. And so in this case, we want the 1,000 grams on the top because we want to cancel the grams that are on the bottom here. So 1,000 grams goes on the top, 1 kilogram goes on the bottom, and so grams are going to cancel. And we have now the solvent, which is water, in kilograms. And that's what we want to have on the bottom. We want kilograms of solvent here. So now we're ready to plug in and do the math. Yes?
On the test, we don't have to remember those boiling things.
Those what things?
Those numbers for the boiling.
No, I will give you boiling temperature and the constants too. The boiling and freezing points and the boiling and freezing constants. You don't have to memorize those. Okay, so when we do the math, we get 8.05576.82.383. The units of measurement we have left are moles of this ethylene glycol, HOCH2CH2OH, over kilograms of the solvent water. Okay, so all the numbers have been taken care of here, but the units of measurement we need to keep here in this fraction. But now we're going to round it off to the right number of significant digits. You're only going to look at the measured or calculated numbers, Chandler, in the problem to figure out how many significant digits you want in the final answer. So this has 4 digits. This measured number has 4 digits. This one has 4. This calculated number has 6. All we want to do is to find all those measured or calculated numbers, the one with the least digits. These other numbers are not measured or calculated. They're counting numbers. So these two have 4 digits. That's the least digits. We want 4 digits in the final answer. 1, 2, 3, 4. Underline from here over to show those are insignificant digits. Draw an arrow that shows that's the operator that shows or communicates that we're rounding off. And the answer then is 8.056. And since moles of the solute per kilograms of solvent is the unit we call molality, we can simply replace these units here with M, and we can call this I'm sorry, you're right, M HOCH2CH2OH solution. Okay, you don't have to name the solvent if it's water. It's used so much that we just, if it's not mentioned, we assume the solvent to be water, and we can just name the solution for the solute. In this case, ethylene glycol. So that's our M amount. That we're going to plug that into this equation for M. So down here we're going to have delta T subscript B, the boiling temperature change, equals I. K sub B is the boiling point constant times M. We're going to plug in I. Well, this is a molecule. It's not ionic. It's not acidic. It's a molecule, so I has to be 1. K sub B you look up in a table. It's in your text, and it tells you in the text.
If it's not ionic, it's 1.
Yeah.
Always?
Always. If it's not ionic or acidic. Acids also break up. Okay? So the K sub B that you look up on the table or in your table is 0.512. That's the numeric value. But in the units of measurement are in the column labels in that table, and that's degrees C per mole. And we're going to multiply that times M, which we found to be 8.056 M. And we want to put this over 1 and this over 1 just so that everything's arranged so we can see how to cancel units here and here. So that then gives us an answer for the change in the boiling temperature. This is the change in temperature, not the actual boiling temperature. Let's see, it's going to come out to be 4.12467 degrees C. We're going to round off, and this number is a calculated number. It has 3 digits. Leading zeros are not significant, so all the significant digits are 3, and this one has 4, so this is the least digits here. We want this answer to have that number of digits, 3 digits. So we're going to round it off to 4.12 degrees C. That's our change in boiling temperature.
Where you get the
The one here? This is a molecule. Molecules always have a Van't Hoff factor of 1. Now we're going to plug it into this last equation that we said we needed, this one here, where the change in temperature is equal to temperature final minus temperature initial. Alright, so delta T we just calculated. It's 4.12 degrees C. T sub F is what we're trying to find. We don't know that yet. T sub I. This is either the boiling or freezing temperature of the pure solvent. It's always the pure solvent that you're using as your initial temperature. Okay? So we're working with a solvent of water. It's on the bottom of the fraction here. And water's initial boiling temperature, that is the boiling temperature of pure water, is 100.0 degrees C. And just as we did in the last unit, this is where we want to isolate the unknown. So we've got an unknown right here. Now in the last unit, all of our isolation steps were multiplication, division. This is addition and subtraction. If we're subtracting 100 here, then we need to add 100 to this side to get rid of it. So I need to add 100 to this side as well. Whatever you do to one side of the equation, you must do to the other. So we're adding 100 to both sides of the equation. That gets rid of this number entirely. This negative number plus this positive number gives us a 0. And so all we have left are T sub F. Over here, we've got 104.12 degrees C. Again, we've got an empty slot right here. So we've got to round off that last digit. And our final answer then, after we round it off, is 104.1 degrees C. And that's the final temperature for boiling for this particular solution. Okay? Any questions? Trey, you got any questions? Did you write all this down? If you didn't do your homework and you didn't write it down, how do you expect to do well on the test tomorrow? You know how to do it. Let me write that down. I'm going to write that down. You said you know how to do it. I'm going to put that note on your test tomorrow when I grade it. Okay. Okay. All right. Well, I hope so. I really do. Okay. All right. Do we need to do another practice problem?
Yes,
I think we need to do one like that.
Yeah, Mike said.
Yeah, Mike should.
Yeah, it's time to go out there and do it.
Let Mike know how to do it.
Now tomorrow is the test. Is there any concept review we need to do besides doing this practice problem before tomorrow's test? Huh? Pretty much this is it. Of course, now all the stuff we've learned in the class up to this point are important things to know. You have to know if it's an ionic compound, like we had in this problem, or a molecular compound like we had in this problem. Okay? Say again, Kayla? What? Okay. All right. Yeah, I'll be glad to. All right, let's do a problem then. Or you can work in small groups if you want to, but we need to do this. Yeah, he did say he knew how to do it, didn't he? Yeah. There we go. Now we got the rubber hitting the road. All right, here's your problem.
The problem that everyone is required to do.
He said it,
What do I have to do with Mr. Tubby?
I don't know. Are you a person or a non-person?
I'm an alien.
Everyone, including you, you're a person. You must do it, yes.